At long last, we're ready to put the physics in multiphysics. So what you do in COMSOL is you go down and you right click on your component and you can add physics, for example. It'll populate your list. It's the same list as in the model wizard at the beginning, but now you have an option to add on a few more things. Assuming you've already got one in, and we're gonna in later lectures, what we're gonna do is go through each one of these physics types, and I'll break down exactly what it's talking about and how it applies. But for a very simple case, which is heat transport in solids, what we're looking at is conduction. When you look at the head node for the physics, it's going to show you the domain that it's appropriate for. So, for example, if you had two rectangles, let's just duplicate that quickly, and I'm going to offset this by, say, 0.15. Let's just do that. So now we have two domains here. We can zoom out, right? What you can actually do is say that this physics only actually applies. You see how 1 and 2 are selected here? You can click that and it'll select and it'll deselect it, which means that you can say certain physics only applies to certain parts of your component, which is very, very useful if you want to do fluid structure interactions. Structures have elasticity, fluids have Navier-Stokes. Generally, you don't mix those two, so you can have a lot of savings with that. Very, very useful. If you expand this chevron on your settings tab here, settings pane, you get to see the equation that it's solving. So it's a very general form of the equation, and I'll break it down in further videos. But the important point here is that we're doing Fourier heat transport, i.e. we're doing divergence of a vector field. That vector field is heat conduction, which is given down here. Negative thermal conductivity, grad T. It will ask for a reference temperature. In some cases, you can look at the discretization. We don't need to worry about that. This is the finite element type that it's using, and certain physics will respond to certain types of elements differently. But COMSOL will largely handle that for you. Underneath that physics tab, underneath that physics node, is we're going to be breaking down effectively the terms and the components of the equation that we're looking at. So the first one is going to be the solid. This is actually the bulk. I'm just going to get rid of this guy again for clarity. Yes. Okay. So the solid is the bulk of the material. What you want to say, so you can show the equation, but it looks very similar. What you need to know there is, for example, the thermal conductivity inside the bulk of the sample. There might be some other properties. Here is density and heat capacity. This particular example that I have up is the tutorial problem for the first week. We are doing a steady state, which means that rho and CP are not required. The heat capacity and the density aren't required. That's why they put them in here. This is the place where you could also say it's from the material, in which case it's going to pull whatever material you loaded into your materials tab up here and automatically apply that. So that's very useful in the future. Okay, your initial conditions is literally your initial condition. For steady state, what this turns out to be is your initial guess at the answer, and then you're going to iterate towards that answer. For a time dependent, this is going to be your T0 case from which you're going to be time stepping forward. Now, the different nodes are the different options that you have, and they're not necessarily all going to be enabled. So what that means is when you look over here for axial symmetry, because we're doing an axisymmetric geometry, there's this nice dotted dashed line here that represents that domain. But we've offset our geometry from that domain because we're doing an annular pipe in this case. So there aren't any boundaries. These are all the boundaries that this boundary condition might apply to, but none of them actually coincide with that axial geometry here. Therefore, it's not used and not applicable for all of these. Thermal insulation, we can see these particular segments on the boundary have been selected, so that's where it's applying to. And then if you look over here, you see that some of these are overridden. And it literally says overridden because the ones below it are specifying different conditions. Okay, the order of these is not arbitrary. It goes sequentially, and the later ones will override the previous ones, which is actually a useful feature, to be honest. So what you would want to do for a Dirichlet condition, which is a fixed temperature, you would go in here and you would actually specify what temperature. Note that you have the units in here too. If you had something else, so again, just to emphasize the units here. Okay, you see how I put C there and now it's squiggled? It's because it doesn't know what C is. Instead, what you would have to put is deg C, which is degrees Celsius, and now it's actually going to take 273 degrees Celsius instead of Kelvin. Okay, that's the beauty of the unit handling, because it'll keep all that consistent. Heat flux is a different type of boundary condition, and again, we just select that boundary and we put it in there. Let's see. If we had selected one of these cumulative selections from the geometry, we would actually have that as an option in the selection. So up here, we're specifying which boundary in particular, but we could also say this selection, in which case it's pre-populated all of the boundaries that were defined in this set. Okay.